Hello, good evening, all.
Good
Good
evening,
evening,
ma'am.
ma'am.
Yeah, good evening. How are you, everyone?
Fine, ma'am.
Fine, ma'am.
Okay, we'll start the session. Let me introduce myself first. So I think everyone know, right, about the Proby logic. So first, welcome to Proby logic, everyone. I'm so happy to have you all here as we start this exciting journey into VLSI technology. Together, we learn, grow, and explore amazing opportunities in the field. So, coming to Provi Logic, our goal is to help students and professionals build the skills needed to the succeed in the semiconductor industry. We are here to bridge the gap between the industry and the standards of academics. Coming to our vision is to make a Provi Logic as a global leader in VLSA training. We want to empower all of you to excel in this fast growing industry to make a mark in the world. Am I audible? Everyone, it's clear, right?
Yes, ma'am.
Yes.
It's clear.
Okay. So our mission is to deliver high quality sessions that focuses on the area where students usually face challenges. And also we need to give our industrial standard job oriented programs at a very high affordable budget for every student who can afford by every student. Coming to the visionary behind the Probi logic, first of all, I want to introduce myself. I think you already know I'm the founder and CEO of Probi Logic. And coming to the Vishwa Arya, he is the co-founder and marketing head. He is one of the backbone of our company. Vishwa Arya is always share great ideas and motivates me. He plays a big role in shaping the success of Provi Logic. He is also my brother. So we both founded this company. And coming to myself, I'm the founder and CEO of ProviLogic. I have extensive expertise in system on chip verification, debugging, and RTL design and verification. I am specialized into system Verilog and UVM methodologies, which has allowed me to work on complex projects in system on chip level and also ASIC designs and also to develop various IPs. As a passionate trainer, I had the privilege of mentoring over 2,000 students, helping them success in their careers with an impression of 85% placement rate till now. My journey in the VLSI industry started with working at leading companies and also served as a co-founder and managing director of Semi Design. With a strong passion for teaching and guiding others, I look forward to work with all of you and helping you to achieve your goals in the dynamic world of VLSI. So we start our agenda of the session today. And today we are going to discuss what is meant by VLSI and what is the VLSI technology, the key milestones of VLSI evolution, and what is meant by Moore law, whether it is executing now or it's dead. And VLSI design flow, what are the career opportunities in VLSI, whether it's a front end domain or back end domain? And what is the difference between ASIC chips, FPGA chips, and system on chip design? And also, finally, we discuss the career guidance and open forum for question and answer discussion from your side. So this session mostly helpful for the students who are looking to start their journey in VLSI. So if you have any doubts in the middle of the session, you can ask your doubts. Okay, it's a totally interactive session, the live discussion session. Whatever the doubts you have, I can answer clearly. Okay, so don't hesitate to ask your doubts. Okay, so we'll start the session. Can you tell me before that what is meant by VLSI?
Very large scale integration circuit, ma'am.
Very large scale integrated circuit. Okay.
Yeah.
So what is meant by very large scale integrated circuit?
So it's meant it is storage depend upon capacity, storage capacity. I say we are considered as very large scale integration circuit. After that, low scale integration circuit. It's totally storage capacity based
Just
on.
a second. Reminding all, can you mute your system? If you want to talk something, then you can unmute and you can talk. Meanwhile, you can mute. Yeah, please go on.
Fabricating free space.
Yeah, please go on. Someone answering, right?
Fabricated in free space, ma'am. In single space.
Single space. Okay.
Ma'am, large number of transistors are integrated as a chip. Ma'am.
Integrated as a chip in a chip. Okay. Any other answers? Okay. How do we get the name of VLSI? What is the before transistor technology? What is the before technology we used in circuit chip design?
Vacuum tubes, ma'am.
Vacuum tube. Okay. Vacuum tube is the first technology developed in olden days in 18th, 1900 century, 19th century. So after vacuum tube technology, you already know how the vacuum tube technology, the where we use different computers in olden days. In your childhood, we have seen a big size of computers. In that, we will find some like long tube like this, right? So that is nothing but vacuum tube technology. Later on, from vacuum tube technology, slowly different type of circuits, small circuits components are introduced, like a diodes. You already work with the diodes, right, in your laboratory. From the diode is also a type of switch. Okay, but that is a basic component, whether it's a digital or analog. So from the diode, we just move to the transistor family. Okay, so transistor also work as a switch. In transistor we have different types, like analog transistors. If you see BJT transistors out there, in digital side we have a MOSFET transistors, JFET or CMOS FET transistors out there. These are various technology developed from last few years, so many years. Okay, so the first what is the birth of semiconductor industry? In 1940s and 1950, in 1947, if you see, the transistor is invented in the Bell laboratories, right? So by the in terms of to get the modern electronics, so in 1947 it has invented, and then in 1958 Jack Kilby from Texas Instruments developed the first integrated circuit. And then in 1959, Robert introduced some other concept like a planar integrated circuits. Nowadays also we are using planar integrated circuits like a CMOS. Okay, CMOS is also one of example of planar integrated circuit, and also there are it's a scalable production. Okay, so that is what the future, the evaluation of semiconductor industry, and then now that we just moved to the era of small scale integration from using a single transistor. Just in olden days we just use a single transistor. By using that we stored some data, we did some operation, very basic operation, do the arithmetic operation, just subtraction, addition, 1 plus 1, just 2 plus 1, a single bit addition operation. Later on, the integrated circuits getting lot of changes, advancements are getting. Okay, like a small scale integration in 1960s, the small scale integration has introduced where we can integrate 10 number of transistors in a single chip. That is a basic chip. From then, every technology, like a small scale, medium scale, like that, the classifications are coming into the picture. Okay, so Small scale in the sense only 10 number of transistors which are used for logic gates. Okay, if you see in your digital electronics subject, the logic gates can be converted into the CMOS transistors, right? By using the PMOS and NMOS, we have connected the CMOS transistors for gate and gate or gate. Okay, so how many transistors will be there? Suppose AND gate is there will be one CMOS. One CMOS means two PMOS, two NMOS connected in parallel and series. Okay, so like that, in small scale integration, just logic gates are developed. Okay, and then medium scale. Medium scale means a nearly 1,000 to 100 to 1,000 number of transistors are integrated in a single chip. So like a small type of multiplexers, there is a difference between logic gate and the multiplexers, decoders, encoders, somewhat complex circuit compared to the gate, right? So by using a medium scale, these type of circuits are designed. And then large scale integration. Large scale integration means a nearly 10,000 number of transistors to lakhs number of transistors are integrated in a single chip. So from here, slowly developed the computers, the gaming consoles, some video game consoles. Here the Moore law came into the picture. Okay, so what is a Moore law? Moore is he is the co-founder of the Intel company, right? So he predicted some statement. Can anyone tell what is the statement predicted by Moore? So if you see from small scale to medium scale and large scale, coming to the large scale, he observed that every classification, the number of transistors on a single chip are increasing. Okay. At the same time, the size of the transistor is going to reduce. So that is what he predicted. So from large scale integrated circuit onwards, the number of transistors are doubling for every 2 years, approximately 18 months. Okay, so that is what the prediction in large scale. And coming to the very large scale integration, here millions of transistors, okay, billions of transistors are integrated in a single chip. By using a very large scale integrated circuits, we are able to design some advanced processors, advanced CPUs, GPUs, whatever we are using nowadays, not nowadays, before 10 years back. Okay, so there we use the VLSI, actually, very large scale integrated circuit, okay, where millions of transistors are integrated on a single chip. So after that, still it's moving. Okay, so next thing is an ultra large scale integrated circuit. Ultra large scale means 1 billion transistors are integrated on a single chip. So by using ultra large scale integration technology, we can develop a more advanced system on chip designs. Okay, not CPU. CPU is just a processor, but now we can design a system on chip. That means every functional block can be inbuilt on a single chip. Okay, before technology, we need to take some components and we need to place on a PCB board like that. Okay, but system on chip means on a single chip, we will integrate every functional block like memory block or CPU block, GPU. There are different interconnections out there. Okay, so those type of circuits we can design in the ultra scale. And also CPU, memory, peripherals, all these things comes into the picture. So after ultra large scale, now we are able to design some nanometer technology. From 2000 onwards, we moved to the nanometer, right? So 1000 nanometer technology, 500 nanometer, 100 nanometers. Okay, so currently what size of transistor we are using in our mobile phone processors or in laptop processors?
5 nanometer.
Ma'am, 3 nanometer.
Okay, so 5 nanometer, 3 nanometer transistor technology we are using in the current processor or any laptop or mobile phone, right? So from 100 to 50 or 45, 10, from 10 to 5, like that, every
Ma'am,
technology reducing the size of the transistor. Okay, yeah, please tell.
ma'am, what does it signify? 5 nanometers means it is a dimensions or
Yeah, we will discuss. So that is what 5 nanometer. Actually, what is meant by nanometer? What we are going to calculate exactly. So nanometer, we are telling the size of the transistor. Okay, so in the large scale integration, we told thousands of transistors are integrating in a single chip. In very large scale, 10,000 or billions of transistors are integrating on a single chip. Ultra large scale, millions of transistors, like that. Every time the size of the transistor is increasing. Okay, so at the same time size is reducing. So suppose this is a processor. Here 100 number of transistors are integrating, and in VLSI thousands of transistors, that means very small number of transistors are integrating. And here in ultra large scale, billions of transistors, that means dots. Nanometer means what is the size of the nanometer? Can you tell me how it look like? It's
10 power minus
very
9.
very thin. Okay, even it's thinner than our hair follicle. Okay, so that is what the transistor size. So here you understood the concept, right? How the number of transistors are increasing and size is reducing. If size is reduced, then only we can integrate those many number of transistors on a single chip. Okay, so we have different technologies in the transistor like CMOS FET, FinFET, GAFET. Okay, so what actually the size of the transistor means? If I consider the CMOS, there will be a source, drain, and a gate, right? For BJT, we have a different terminals, base, emitter, collector. For
Yes,
CMOS FET,
correct.
we have a source, drain, gate. Okay. So how the current flow happens between the how the current flow happens in the transistor?
Emitter to collector, ma'am.
In CMOS.
In CMOS, gate introduce current,
CMOS drain to
source to drain.
The current flow is in the direction of source to
To
drain.
drain, it will be controlled by gate.
That will be controlled by gate, and there will be a channel here. Okay, the
Yeah, ma'am.
channel in this way. Okay, it is thicker at source side, and drain side it is a thinner. Okay, so this is what the channel size. So here what is the size of the transistor? So here we are telling 90 nanometer or any nanometer size of the transistor, right? So we size of the transistor means we want calculate whole transistor size. Okay, the width of the distance between the source and the drain, that means channel width, nothing but size of the transistor. Okay, so 90 nanometer transistor means what? The distance between source and the drain is 90 nanometer here. Okay, so if 50 nanometer means the distance between source and the drain is 50 nanometer. Okay, 10 nanometer means the distance between source and the drain is 10 nanometer. So if you observe something here, source is a conducting material, right? It's a semiconductor material. If you see in your academics, you will find everything, how the doping is happened, the base and gate, how the connections will be happened, the metal semiconductor materials, how the doping, everything you will get understand if you go to in-depth, okay, concept like a structure wise concept. Okay, so here source is a conducting material, drain is a conducting material. Whenever the size of the transistor is reducing, so it's a 1000 to 100 to 50 50 to 10 to now 3 nanometer size we are using, right? So whenever the distance between source and the drain is reducing, both are conducting materials. Okay, at some certain point of time, if both conducting materials are short circuited, what happens if both are getting a very closure, right? So then what happens? What are the limitations we can see?
Power loss.
Power loss. Okay, and then
Stroke.
sometimes the transistor, if transistor current is flowing in this direction, if both are short circuited, it may go in this direction also, right? Into the gate, it tunnel into the gate, right? That is one type of chance. So there will be loss current lossage will be there. Short circuit effect will be there. Okay, so these are the various limitations we are observing from past 20 years, whatever the technologies are changing. Okay, so what is the transistor technology we use to fabricate a chip? What is the transistor technology we use? Like we have BJT, MOSFET, JFET, CMOSFET, like that, right?
MOSFET.
FinFET.
CMOSFET, FinFET. Okay, suppose if we use a CMOSFET example, CMOSFET is at a 100 nanometer technology, okay, at a 50 nanometer technology, suppose. So if we see, you already understood the Moore law, right? Is it clear, everyone? What is a Moore law?
No, madam. Modla, I didn't get.
You didn't get, huh?
Yeah,
Okay. Moore law is nothing but this is what I have draw here. Um, um, Here is a chip. Suppose this is a chip. Okay. So if you see in small scale integration, we integrated 10 number of transistors in a single chip. 10 number of transistors means what? In digital circuit, if you draw a multiplexer, okay, multiplexer means there will
Ma'am,
be a,
hello.
yeah.
Sorry to interrupt you. But if you're writing on anything, I think I am not able to see if you're sharing on other screen. I'm just
Okay.
able to share your
Is it not
PowerPoint
visible?
presentation.
I'm writing something here. Is it not visible, everyone?
Yes, ma'am.
Oh,
Not visible, ma'am.
okay, okay, wait. I think it will be visible now. Is it visible now?
yeah, ma'am.
I'm writing. Okay.
Evolution of VLSI technology. Yeah, visible, ma'am.
Okay. See, suppose this is a chip. Okay. So small scale integration, suppose I'm taking, and for medium scale integration, large scale integration, very large scale integration. Now it's visible, right?
Yes, ma'am.
Yes, ma'am.
Okay. So in small scale integration, uh, we just integrated 10 number of transistors which are in 1000 nanometer transistor. Okay, not 1000 nanometer. In that time we use micrometer level. Okay, nanometer is came to picture in from VLSI only. Okay, nanometer technology, not from small scale. In small scale we used a micrometer and maybe more than that also. Okay, so this is what the size of transistor we used in the small scale integration. So if large number of transistor means how many number of transistors we can able to inbuild that in the chip? Only 10 number of transistors. Okay. In large scale integration, we are going to integrate 1000 of transistor in this size. 1000 number of transistors. So size of the transistor is reducing. In the medium scale, suppose in the large scale 10,000 number of transistors are integrating. So which is in this small size, very small size like this. Okay. And in the VLSI, very large scale, 1 million transistors are integrated. That means this size, very little in terms of 100 nanometer. Okay. So in which year small scale integrated circuit are designed? In 1940s, 1950s, at that time. Okay, coming to 1980, medium scale, or 1960, and large scale 1980, and very large scale 1990. Okay, now what is the Moore law? Moore law predicted that for every 2 years, approximately 18 months, okay, the number of transistors are double. That means from 1950 to 1960, transistors are double from 10 to 1000. Okay, 1000. He predicted only for 2 years, but I'm taking here for 20 or 10, like the 10 years. And here transistors are double. Again, here 1 lakh transistors, or some crores of transistors we are using. And in very large scale, millions of transistors are integrating. That means for every 18 months, number of transistors are double. Okay. And
Are muted, ma'am.
Madam, you are muted. Your voice is not audible now.
okay, I didn't muted, right? Someone muted. Okay. Okay, fine. So if you see, if you observe, every 10 years, the size of the transistor is reducing. If you see here micrometer, and here some 100 nanometer, and here some 50 nanometer, and here 10 nanometer, the size is reducing. Okay, Moore law is nothing but reducing the size and also increasing number of transistors for every 2 years. Is it clear now, everyone?
Yes, ma'am.
Okay. And someone who asked the question, is it clear?
Yes, ma'am.
Okay,
Yes.
so this is how, if you observe in terms of picture, in 2002, how the picture size, 2.6 micrometer technology used here, and the size of the chip also very big. Okay, it's a complex. And 2004, 4.4 micrometer, and then 2006, 7.3 micrometer, 2008, 11.2 micrometer, and then from micrometer to nanometer in 2012, 28 nanometer, 14, 20 nanometer. That means size of the chip is reducing. That means size of the transistor is reducing. Number of transistors are more. What is the benefit? What is the advantage of increasing more number of transistors in a single chip?
We
What
can
are
do
the
more operation.
more operations? Okay,
Madam, ma'am, power performance area.
power performance. Okay. So
Speed of
multiple
operation.
tasks can be run. Okay, so switching operations will be more, right? Here transistor is nothing but it's a on and off. If it is a on, we store 1 bit data. If it is a off, we store 0 bit data. Okay. Suppose in small scale integration, there are 10 number of transistors, means what? Only 10 number of times it do off and on, off and on. But coming to where we use the billions of transistors, billions of times we get the switching operations, right? So transistors will do switching operation those many times. That means the fastness of the chip automatically increases. Okay, and the power consumption is also increased because we are using more number of transistors, but the size is less. Bulk in hello. Am I not audible?
Audible, ma'am.
Okay. So that is what the advancement of the VLSI chip. Okay, so whenever we increase the number of transistors in a single chip. So if you see here, we use different fabrication technologies in the VLSI. Okay, like a planar FET. Planar FET is nothing but a CMOS FET. Okay, so in the CMOS FET, there will be a source, drain, and the gate. Okay, here the green color is a channel and this violet color is a gate. Okay, so here the current is passing from source to drain. Before I explain, right, the size of the transistor is nothing but the distance between the source and the drain, also called as channel width. So hello, whenever the channel size is reducing, please mute your systems. If you are not interested, you can leave. Don't disturb the session. See here. So whenever the transistor size is reducing day by day, suppose if it is 100 nanometer or it is a 10 nanometer or 3 nanometer, but basically CMOSFET is up to 25 nanometer only. Beyond 25 nanometer, it faces lot of limitations. Why? Because source and the drain is coming to near, right? Both are very closer. So limitations are getting like a gate tunneling limitations. As I told before, the current is flow in this direction into the gate at atomic level. Okay, so those type of limitations are getting when it is in a 25 nanometer technology. Okay, so like short circuit effects. Okay, and power losses. These are the lot of limitations are facing in this 25 nanometer technology. And then just make the small changes of CMOS, just as small modifications. Like here, whatever the channel is there, the channel is taken into the 3 gates on a single channel, like a fin manner. This is one fin and second fin. Okay, so that there will be more controllability on gate, source, and the drain. Okay, there will be 3 number of gates in the channel. Okay, so that we can control the transistor current without doing the without going to short circuit effect, and it doesn't tunnel the gate. Okay, so that is what the FinFET transistor technology. Okay, so planar is still 25 nanometer only, and then from 25 beyond 25 nanometer FinFET transistor is introduced to avoid the limitations whatever we are facing in the CMOS. Okay, and after reducing 25 to 20 nanometer, 20 nanometer to 18, 18 to 15, sometime, okay, whenever we are reducing the size of the transistor, at some point of time in FinFET also getting the limitations. Okay, same limitations like a power loss, the current short circuit effects, and also the circuit is the transistor tunneling into the gate. Okay, at atomic level, these are the limitations we are facing again. So from the FinFET, another transistor technology has introduced at 15 nanometer beyond. Okay, so the transistor technology called gate all around transistor. Gate all around means what? In FinFET, only 3 number of gates are there on channel. Okay, so that's a less controllability whenever the more transistor is reducing more. Okay, so next, beyond 10 nanometer or 7 nanometer, the gate all around is introduced. Here we didn't use uh, any channels here. These are just nano sheets. Okay, here we use the nano wire, and here nano sheets, very thin nano sheets, so that it is a good controllability on the current. Okay, so we just avoided some limitation in the gate all around by taking the nano sheets. After gate all around also, we have lot of technologies like a MACFET, MBFET, like that, where we use multiple thin nano sheets. We are trying to avoid the short circuit effects. Okay, so that is what our main goal at the fabrication side in VLSI. Okay, but now we are in the generation of 3
Hello.
nanometer transistor technology, right? Hello.
Sorry to disturb, ma'am. May I ask a question?
Yeah, please.
Aren't we increasing the length of channel? Like the green area is increasing from planar FET to FinFET to gate all around. I
uh,
can see the boundary parameters increasing.
it just is showing in the picture. but it's not actual size. Just for representation of structure, it just looking like that. But in real time, we have a very minimum size, like 10 nanometer to 3 nanometer, whatever the size different is there, same it will be there. Okay, but just representation of structure, it is looking like that, like a same.
Okay, okay. Thank you, ma'am.
Yeah. Okay, so 3 nanometer. In 3 nanometer, we are using different transistor technology, fabrication technology. Suppose if transistor reduced to 1 nanometer means like this, very thin, nearly short, both are short circuited. Okay, so what is the technology we can use there? So if both are only 1 nanometer means, what is the next? What is the future of VLSI?
Ultra scale.
Ultra?
ULSI now.
ULSI already completed. VLSI is last 10 years VLSI till 2000 at that time. Currently ULSI also we reached. Okay, we crossed.
Mono electronics.
Nano electronics. Okay, in nano electronics, what type of
Uh,
technology?
mono electronics.
Okay, so what type of technology we can use over there? Same, we store the data into transistors and same fabrication technology, same chip designer, or is there any advancements? So lot of news we are getting, right, from social media or whatever, like VLSI is going
Maybe
to dead.
quantum,
Yeah, please tell.
maybe quantum tech will be used. Qubits and
Quantum technology. Okay, so how the quantum technology works?
Qubits.
Through qubits. Okay, so what is the difference between normal bit storage and qubit storage? What is the performance speed?
Ma'am, so qubit storage in there, there are set vectors which can be like in quantum state, it can have an all different energy in all different levels, but bits are only limited to zeros and ones. But it can be on and off state, zero and one state, example.
Okay, so qubit means suppose in normal classical computers we use either 0 or 1 to power n number of combinations. We cannot do parallel operations, but by using the quantum technology we can do parallel operations. All combinations we can run parallelly, so that is one of the main advantage. Another thing is a nanometer neuromorphic chips also. Okay, neuromorphic chip is also one of the advanced technology in VLSI. Maybe in next generation, next 5 to 6 years, we get the neuromorphic chips also. It is in like a development stage, right? So where we use the deep learning techniques and machine learning techniques, how the human brain is working. Okay, so our brain gives every instruction to the body, right? To do something, to write something, to talk something. So every instruction is given by the brain. Okay, like that, from childhood onwards we tell like CPU is the brain of the computer. Okay, but actually it works like a brain. Okay, but we design the CPU by using the instructions, right? We have assembly language programming. If you see in your processor, microprocessor course, in your subjects academics, there will be a high level assembly level programming, assembly language programming, right? There we write the multiple number of instructions: add register 1 comma register 2, source register, destination registers, like that. Okay, so that is what the assembly language we use to design a processor, to design a core. But we didn't use any brain structure in the VLSI chips till now. Okay, but in neuromorphic chips, however, the brain structure is there, Okay, with the nephrons, neurons, everything, how the connections are there with synapse, everything. So that is what the structure we are going to bring in the VLSI. Okay, so that is one technology is there, the future of technology. Another thing is a quantum. And quantum, there are some 3D ICs. Okay, some 3D type ICs are going to come into the picture. Maybe we don't know which one will um, get into the market. Okay, because all are in developing stages, right? So which one will get click into the market, we need to check, see, we need to wait. Okay, like AI chips. Mostly nowadays we are using AI chips, right? Chat GPT is one of the AI application, and also most of the chips we are using AI applications only. So these are the different advancements we are going to get in the future. Okay, so maybe the semiconductor material, whatever we are using here, the normal technology, maybe it will die, but we have lot of advanced technologies in the VLSI. Okay, so that is the future of VLSI. We are going to a new era in VLSI if it is reached to 1 nanometer. Okay, um, so everyone clear up to here? Did you got the point? What is mean
Ma'am,
by VLSI? Yeah, please tell.
could you tell me about FinFETs, ma'am?
Yeah, please tell.
Ma'am, could you tell the operation of the FinFETs?
See, FinFET or CMOSFET or GAFET, everything is a transistor. Okay. As I told, the transistor sizes are reducing day by day, right? So whenever the transistor size is reducing, we are facing lot of limitations, right? In CMOSFET, at whenever it is 25 nanometer, in 25 nanometer, we face lot of limitations because it's a planar, it's a planar like this. Okay, so in 25 nanometer it's a very minimum distance between source and the drain. So that's why, to avoid these limitations, in the FinFET, same channel we took into the fin like this, same channel just designed in a fin manner. Okay, to avoid the limitation. Why? Because in the planar manner we are not able to control the gate. Okay, because there is a only one gate, there is a short circuiting effects, so the current flow is going to tunnel into the gate like it, like this. Okay, so the gate is not able to control the flow of current at that stage. Okay, so to control the flow of current, just a gate, whatever the channel is there, we just make some few changes structure wise only. We just make the changes, we didn't change any material, nothing. Just a structure wise, whatever the planar manner is there, that planar channel we took into the fin manner. Okay, so that the gates or three different gates are created, same material, same thing, but three different three gates are created, so that the current flow, whatever the current flow is there between source and the drain, the gate can control. Okay, without tunneling the current into the gate. Okay, tunneling into the gate means what? The current flow should be the source and the drain like this, but the current is going to into the gate like this. Okay, if it is going into the gate like this, in the CMOSFET, the gate cannot the gate is not able to what we tell manage the current flow. Okay, current flow is heavy, right? So that's why the gate cannot stop. That's why here we are creating three different gates where the gate can stop without tunneling the current into its through the gate. Okay, so that's why here three different fins are created as a gate. Okay, even whenever it created as a fin at 15 nanometer, it is working fine at a 15 nanometer. Okay, but whenever it is reducing from 15 to 10, 10 to 7, okay, again the short circuit effects are getting, because the gate is losing its property, it's a behavior, right? Whenever the flow is very high, the gate is going to lose its property whenever it is reducing, the size is reducing. Okay, so from FinFET, GAFET is created. In FinFET, these three are nothing but wires. Okay, so from the wire in GAFET, sheets are created, nano sheets. That means 4 gates. If you see here, 3 gates and backside 1 gate. 4 gates are controlling the current flow here. Okay, without tunneling the current into the gate, without tunneling the flow of current into the gate. Okay, 4 different gates are controlling, so that we get the proper operation. Proper operation means what? The current flow should be between source and the drain, then only the transistor either on or off, right? But after gate all around, it is at 7 nanometer. But after 7 nanometer, again transistor is reducing 5 nanometer, 3 nanometer, like that, right? So at 5 nanometer, the gate all around technology is not work, because again the gate loses its capacity. Okay, so again we should have some more technology. Okay, without losing its capacity, it should able to uh, it should able to fight with that current flow, right? It should be very strong. Okay, so that's why here 4 gates are created. And then MACFET, there's some more nano sheets are created in MACFET, MBFET. And then this is how the transistor technology is increasing. Okay, fabrication technologies, different technologies internally, these all just open source, but internally what AMD using the technology, what Intel is using the technology, we don't know. Okay, so that those are official things in the companies. Okay, so did you got the point now?
Yes, ma'am.
Is it clear, everyone?
Yeah, ma'am.
Yes,
Okay.
ma'am.
So that is what I think everyone got the clarity what is mean by Moore law, what is mean by transistor, and size of the transistor, how to calculate, and how the transistors are integrated on a single chip. Right? Is it clear, everyone? Any doubts?
No doubt, ma'am.
Okay, fine. Next,
Ma'am,
next is please tell.
ma'am, can I ask one question, ma'am?
Yeah.
Ma'am, if you increase the quantity of transistors, there is a disadvantages also. Like transistor is a non-linear element, so if it will generate a high amount of noise because of its non-linear characteristics. So if you increase the quantity of transistors, automatically linearly increase the noise also. Then how to overcome that problem?
See, we have a lot of internal flow. Suppose you asked noise integration, everything, right? So we have the techniques, different noise reduction techniques will be there in the physical design. Okay, so some UPF techniques will be there. Some power analysis techniques will be there. So by using all these things, we get a proper output. So both analog and digital, both things are involved in a circuit, right? So internally there will be lot of sub domains in VLSI. Okay, if you go through this, you will get the clarity from here. VLSI design flow. Okay.
Okay, ma'am. Okay. Thank you, ma'am.
Yeah. So coming to the VLSI design flow, till now we have discussed what is the size and how we are integrating number of transistors in a single chip, right? What is the Moore law? But to design a processor, to design an integrated circuit, it takes lot of time. Okay, so one processor will take at least 2 years of time from front end to back end if we want to design. Okay, even if there are lakhs of engineers working together to develop a single processor, to manufacture a processor, it takes some time and it takes various stages. Okay, so to design a processor, the lakhs of engineers involvement will be there. Okay, and it divided into sub fields. So if you are VLSI aspirant, if you are very interested in VLSI design, first you need to understand the area of interest. Okay, so which area of interest you are? If you are interested in front end domain or back end domain, whether you are interested in coding side or non-coding side. In the back end, mostly the manufacturing tools, we will work with the tools. Okay, so you need to choose your area of interest. Okay, so from this VLSI design flow, you will get the clarity how to choose a specific domain. If you are VLSI aspirant, if you are looking for some course, if you are looking some to get into the job into the VLSI, if you want to settle here, you need to understand what is the flow. Okay, so see here, there are different subdomains in the VLSI. Majorly, front-end domain, back-end domain. Okay, so front-end domain means developing some architecture in a tool, just writing the code and developing the netlist in the front-end design. Back-end design is a manufacturing process. Okay, manufacturing process in the sense everything we design in a hardware level, in a silicon level, we design everything. Okay, and coming to DFT insertion and logic synthesis, we will discuss one by one clearly what is mean by front end domain and what are the different subdomains are there in front end domain and what are the subdomains in the back end domain, so that you will get the clarity. Okay, so next thing is coming to the front end domain. So in front end domain, if anyone want to manufacture a processor, whatever it's any brand, whether it's a Ryzen processor or any Intel processor or Samsung related processor, Snapdragon, whatever the integrated circuit, in industry, how the things exactly happen means, first the specification we need to consider. Okay, specification means what? Suppose you are using a mobile phone, so iPhone, suppose iPhone have some generations, right? 13th generation, 14th generation, 15, 16. So every generation have some advancements and some best features are introduced. Okay, so like that it will be happen. So according to the features, whatever the new features are added and whatever the unused features are there, they can remove the features. Okay, so specification means writing an overview of a project. Okay, taking the overview of the project in terms of memory. Suppose overview I am telling, uh, we are using some different size of memory, right? A 128 bit or 256 bit. Okay, memory backup. What is the memory backup? In terms of camera, what is the size, pixels, number of pixels in camera? And in terms of processor, how many number of cores are there? Okay, and uh, what is the performance? What is the battery life? Everything we check, right? So overview in specification, we will take a design functionality. Okay, theory wise, just in a paper we just take. Okay, so according to the specification, we draw the overview of the circuit or just a block diagram. Suppose simply, if we say simply, uh, you want to design a multiplexer. Okay, so multiplexer means what? First, you need to understand the functionality of the multiplexer. Suppose it's a 16 by 1 multiplexer. So you need to understand what is meant by 16 by 1 multiplexer. And then you need to draw the block diagram. So 16 by 1 multiplexer means there will be 16 number of inputs and there will be one output and there will be n number of selection lines, control signals. Okay, so this is what the overview of the diagram you will get. Okay, from this you need to design a architecture. Okay, how we will design the architecture in real time? Architecture means, suppose it's a processor, it's a chip. In the chip, there will be a processor, there will be a memory blocks, and there will be some graphic processors, and there will be some interconnects and camera modules, GSM module, Wi-Fi module, Bluetooth module. There are a lot of. Okay, so in the same way, we will design a block diagram. Okay, so from the block diagram, we need to draw the circuit. How we draw the circuit diagram? Can you tell me what are the steps we need to follow? What are the steps we need to follow to draw a circuit diagram from the specification?
Number of inputs and outputs.
We just take the number of inputs and outputs. According to that, we draw the truth table. Okay, so
Yeah.
truth table means what are the inputs and what are the outputs according to the functionality, what is the output. So here we get the output. So we from the output we write the expression, output expression. Whether we can use the SOP format or POS format, we write the output expression. From the output expression, we draw the circuit diagram manually. Okay, just with a
Yes.
pen paper, we just draw the circuit manually. Okay, so we get the architecture design. From the architecture design, we need to design this in terms of software, in terms of tool. Why? Because here multiplexer means it just have 10 number of gates or 20 number of gates, but in real time computer architecture means there will be lakhs of transistors, billions of transistors, millions of transistors, right? So we cannot generate manually. Obviously we need to generate through the some synthesis tools, and we need to verify using simulation tools. Okay, so RTL coding means we will design a architecture by using the hardware description language. We have different types of languages, right? Like a C language is there. It is for high level language. Just to design some games or to design a website, we use Java program or Python program, like that. To design a processor, before I told assembly language programming, right? That is one type of programming. Like that, to design the hardware, to design the digital circuit or analog circuit, we have hardware description languages, okay, called VHDL or Verilog HDL. We can use any language. Okay, mostly industries prefer Verilog HDL compared to VHDL because it has some limitations. Okay, so by using Verilog HDL programming, we design the RTL netlist. After doing synthesis, we get the RTL netlist. After getting the RTL netlist, do we send this circuit to the backend process without doing the verification?
No, madam.
So here right side is a block diagram, writing the coding, circuit diagram. So do we send directly the circuit diagram to the backend process to dump into the silicon? We never do that, right? Because we don't know whether the output is correct or not. We need to verify. We need to check all the signals are connected properly or not. Even if it is corrected, all the signals are connected properly, we don't know whether the output is correct or not, right? So for that purpose, we need to do the verification, functional verification. Okay, we have the functional verification, formal verification, front end verification, back end verification. There are different verification domains out there. So functional verification we need to do in the front end after RTL coding. After doing the functional verification, if if we meet the specification, the functionality meet the specification, that means we got everything clear, output is correct, then we go to the backend process. If the output is not correct, we go to the RTL code again, because there is something error in the RTL coding in the netlist, generating the netlist. There is a something error is there. We need to fix that error. We need to fix the functionality, and again we need to do the functional verification. If it meets the specification functionality, we go to the backend process. Okay, so this is a front end VLSI domain, design verification domain. This is one of the major domain in a VLSI field and popular domain in in India. Okay, compared to physical design, design verification is good in India, but physical design is also good. In next coming days, the government initiated fabrication hubs also, because till now for fabrication we depend on foreign countries. Okay, foreign country companies. But next 5 years, everything will be there in India also. We don't have any dependencies for fabrication also. Okay, so is it clear, everyone, till here?
Yes, no.
Ma'am, which
Others?
domain is more demand, ma'am?
Which domain is more demand means both are good, DV and PD. both are good according to your interest. You can choose. Okay, so if you work hard in properly, if you dedicate your time properly, any domain is good. But in India, design verification have more opportunities comparatively. Okay, but both are good. And coming to the
Ma'am, PD consisting of which
sorry.
PD? What it consists, ma'am? Analog or digital or which one?
See, this is a total digital VLSI. We are discussing about the digital VLSI. We have analog VLSI also, but analog VLSI things are different. Multi-signal processing will be there. Analog signal processing will be there. Analog design will be there. Those are different domains. But in digital VLSI, the main is a front-end domain and a back-end domain. In front-end domain, design verification. In back-end domain, physical design, logic synthesis, and the DFT team will be there. Front end also we have the DFT teams. Like that, there are several validation engineer, verification engineer, formal verification engineer. Like that, domains are divided. But as you are a fresher, you can choose any one domain, either front end DB or back end PD. DFT also good, but compared to DB and PD, DFT have very less opportunities. Okay, so if you want a very good engineer, if you want to become very good engineer, you can choose either DB or PD. Okay, DFT also okay, fine, good, but PD and DB are major. Okay, so
Ma'am, I
coming
have a
to
question, ma'am.
yeah, please tell.
Yeah, so in the previous, ma'am, in the previous slide, you have said about functional verification, right?
Yeah.
So, what do you mean by functional verification? Is that like writing the design and the test code, or is it like?
For functional verification, we have languages called System Verilog and methodology UVM. UVM methodology, Universal Verification. Um, by using that, we write the test cases. Okay, so test cases is to verify the design. That is what functional verification.
Yeah, ma'am. Thank you.
Okay. Next, after whatever the synthesize, after doing synthesize, we get the circuit diagram here, right? So before sending this circuit diagram to the physical design process, here two blocks are involved. If you see logic synthesis and DFT insertion. Okay, so what is mean by logic synthesis? In the sense, logic synthesis transforms high level RTL code, whatever before you written RTL code here, this is what RTL code, that RTL code into the gate level representation. So this is what gate level representation. From the RTL coding here, we get the functionality only, not in terms of gate level representation, in transistor level representation. Okay. Here we get the gate level netlist, GLS, RTL to GLS. If you heard the word RTL to GLS will be there. So from RTL to GLS, physical design also GLS will be involved. Okay. So this is how the logic synthesis, it will convert high level RTL code into the gate level representation, and the the logical expressions, whatever we write, that logical expressions will be converted into the standard cells from the libraries. There will be a lot of libraries, inbuilt libraries. From that, it will convert the logical code into the circuit netlist. Okay. The next thing is a gate level netlist. Gate level netlist means it provides all the detailed representation of the logic gates and their connections. Okay, so that is what gate level netlist, and it serves as the input to the back end of physical design. If you see, it's a input to the back end physical design, right? Same. And logic equivalence check. Equivalence check is nothing but in RTL design, after RTL design, we are doing functional verification, right? Like that, here after generating gate level netlist, we do the verification. That's what we call logic equivalence check. That means it compares the RTL and the synthesized gate level netlist, and also it will check the functionality accuracy, how the synthesis has ensured. Okay, so that is what logic equivalence check. After everything is clear, it is moving to the physical design process. But before physical design process, it involves the DFT also. Okay, we will discuss the DFT. And coming to the physical design process, here right side, if you observe here how the wafer is going to take, and these are the transistors, these are the what the floor planning and how we are placing the transistors in a chip. Okay, so first floor planning. Floor planning means whatever the physical layout is there, we will consider the layout is the silicon material, because one of the best semiconductor material is a silicon, which we can make from the sand. Right, sand is one of the cheapest material, so that's why from sand we can make the silicon material. So silicon material we can take into the physical layout of blocks, and it allocates some logic cells will be there, and there will be some IO pads will be there. So according to that, we'll make the floor plan. After floor plan, placement and clock tree synthesis. Placement means what? Whatever the blocks are there, memory blocks, core design, or some different types of IPs will be there. So all the blocks will be placed with the what is the length. Suppose house plan is there. House plan, every house we have some plan, right? What is the size of each room, kitchen room, how much the hall room size, how much, like that every block will be taken into the size, the what is the size of core, graphic processor size, memory size, hardware level. Okay, and then clock tree synthesis. Clock tree synthesis means it distribute the clock signal uniformly with a minimal skew across the sequential elements. That means we'll connect the clock with the all blocks so that we get the synchronization between all the blocks. That is a clock tree synthesis. And then routing is nothing but whatever the physical connections wire connections will make, right? So that wire connections is nothing but routing we call. Okay, and then static timing analysis. Static timing analysis means internally there will be lot of clock signals. Every signal we should it should match with the clock, synchronize with the output. It have the like whole time analysis and setup time analysis. Okay, so it should meet the requirement of critical timing paths, and sometimes it have lot of violations. So we need to identify the critical timing paths and the potential violations. So whether it should meet all the parts that meet the setup time, setup analysis and hold analysis, we need to check these things. That is static timing analysis. Every fresher need to learn STA, static timing analysis. Even if you are front end domain or back end domain, whatever, static timing analysis is a common. CMOS design is also common. Okay, digital electronics also common. Verilog HDL also mostly, if you're interested, you can learn, that is also common. Okay, so after that, DRC, design rule check we call. Okay, so just it have the layout fabrication rules, the manufacturing rules. Okay, and layout versus schematic, LVS we call. It confirms the physical layout that matches the logic design or not, and the power timing. We check the signal integrity before the fabrication. So that is what in the LVS. And then tape out. Tape out in the sense the main final design. So here we get the final design for fabrication. It include all the layers, and it have the GDS format from RTL to GDS. So everything will be finalized here in the tape out. So after tape out, we get the circuit diagram like this. Okay, so this is what the physical design manufacturing process. Okay, so if you are interested in physical design, you need to learn floor plan, how to do floor plan, clock tree analysis. Internally there will be lot of subtopics will be there. Physical design means mostly mathematical calculations, tools, everything we do in the tool calculations are most important. Okay, so that's what. Clear everyone till here?
Yes, ma'am.
Any doubts? in physical design?
Excuse me, ma'am.
Yeah, please tell.
Ma'am, do we use HDL at any step in the backend?
We don't use in backend. HDL is a programming language we use to design the circuit in the front end. We don't use in backend. But as a fresher, if you learn HDL, that would be good because industry expectations are more nowadays. In before the last 4 years, 5 years, it's not like that. We can crack easily. Okay, if you learn some projects and protocols like the basic things from PD or DV, like minimal, we can easily crack. But nowadays, even if you learn from VLSI design to backend also, it's a good, okay, that will be like a specialization in VLSI. So that will be standard in future. Okay, so whatever you are learning, even if you go for self learning or even if you take some training, try to learn in depth. Okay, try to understand what is the flow exactly happening. Okay, so suppose DV is there. In DV, we must have the very good coding knowledge, but it is not very difficult. It's not like a C language or Java programming, you know. Java is a very vast. C language is also very vast. Even if you write a multiple programming for multiple designs, there will be something new to develop logically. But Verilog, System Verilog or UVM, it's not like that. It's a standard. Okay, so Verilog somewhat logical designs we create, but SV, UVM all are standard. Once you learn in for one different architecture, it is standard for everyone, everything. Just logical changes, functionality changes will be there. Okay, so whatever you are learning, try to learn in depth. Okay, and physical design also same.
Mom? Hello. Excuse me, ma'am.
Yeah, tell.
As the flow is shown, can you please show what are the job roles according to the steps, like
That's what I'm
physical
telling.
design role and
In the
verification?
front end, job role is a design verification only. Okay, in the physical design engineer, that's it. DFT engineer. Okay, for freshers only these three. Okay, if you get some experience in the industry, from the industry you can convert to the SOC design engineer, ASIC design engineer, formal verification engineer, validation engineer, testing engineer. It comes through your experience, whatever the projects you are working in the industry. From the project experience, after to change the next shift, that means to the next company, these domains are helpful. Based on the projects you need to choose. Okay, but for freshers, main domains are design verification, physical design, DFT. That's it.
Okay, ma'am. And one more I have heard is layout engineer. What is that and how it is different from
Layout
design
engineer
verification?
also like same here. Physical design is there, right? In that layout, in the sense these type of things, how we do the placing, routing. So that is what layout is also same. That is a subdomain in a physical design.
And which role is stagnant after some time and continuous growth in which domain, like design engineer or PD?
Both are good. Design verification is good, PD is good, but nowadays market is somewhat less for PD market requirements, but both are good. If you are very interested
Okay.
in PD, you can go with PD, but just try to work more, because if there are 100 number of students means requirements are only 10 to 15. Okay, so whenever you have a good knowledge, not only in VLSA domain, it happens in a IT software and any domain, it's the same thing. But our dedication should be most important. Okay, so So, but VLSI is very good. In next 4 to 5 years, we are getting lot of opportunities even for freshers, experienced candidates. So VLSI is going to rule, right? So if you are interested in core domain, this is the best option I can say. Okay, no need to worry about
Yes,
the
ma'am.
placements and all. No need to worry about the placements and all. First, you need to have good proper knowledge, right? So placements and all you will get once you have proper project knowledge and all. Okay, so initially don't worry we don't have VLSI placements, core placements. It's a wrong totally. Okay, if you have proper knowledge, you can get any way. There are a lot of hundreds of companies out there, thousands of companies. Okay, so next,
Yes, ma'am. Ma'am,
DFO. Yeah, please tell.
how is design engineer and verification engineer different? Like in a group, I have heard out of 50, 2 or 3 verification engineer was there, and mostly were design engineers. So is it like design engineer has more demand than verification engineer?
Verification engineers have more demand than design. But verification engineers are more, design engineers are less. Okay. So whenever you are learning as a fresher, you need to learn both design and verification. If you stuck with the only design means we don't know whether you get the opportunity for design or not. So whenever you are learning design verification, whenever you are preparing for design, learn verification also. But if you are interested for design, your concentration should be on CMOS design, microarchitectures, computer architectures. Okay, so those subjects you need to learn if you want to concentrate on design particularly. Verification means system verilog UVM enough.
Okay, okay. Thank you so much, ma'am.
Yeah.
Ma'am,
Yeah, please tell.
I heard that physical design comes under software based. Like, what language do we use there? Do we use tool command language, or is there any other language that we use there?
In system verilog we don't use any languages. Okay, so everything we develop in the tool. Suppose floor plan is there. Floor plan means what are the chips, what are the circuits are there, what is the size of each circuit, where we need to put each component. Suppose wait. Suppose floor plan, here is a SOC design. In the SOC design, there is a core processors. In the core, there will be a number of cache memories, different number of cores in the processor. There will be a graphic processor and memory blocks will be there. There will be memory controllers, RAM, ROM memories, DRAM, DDR. And there are different IPs like any camera modules or GSM modules or Bluetooth or Wi-Fi modules, and there will be interconnections like this. Okay, so this is how we placed here. Same floor planning means what? Same like a house construction. Okay, so if you see house construction, what happens? First we do floor planning in the sense we get the plan from the engineer, right? If you want to construct a house, before construction of house we get the plan from engineer. That is just a software documentation. Okay, software documentation is nothing but simply see, this is what the specification means. What you want to construct a triple bedroom flat or triple bedroom apartment something. Okay, in that apartment, how many number of floors should have, in each floor how many number of flats should have, in each flat how many number of rooms should have. So that is what the specification. Okay, and each room what is the size. Okay, and total apartment what is the size, and flat what is the size, where you need to put the steps, where you need to put some lift, where you need to put something some whatever the garden and all. So that is what the specification. Features means interior work, where you want to put some extra interior work. That is what the specification you have. Okay, Now with this idea, you have an idea. Okay, with this idea, you will go to the engineer to draw the plan in a software. Okay, so first he will show you how the plan manually in a pen and paper. He just show this is what the apartment, and there will be a number of flats like that. In each flat there are different blocks, rooms. So he will just draw the top level diagram. So that is what architecture design. Okay, so once it is fixed, the same engineer will draw the circuit, will draw this house plan in their softwares. Okay, so after drawing that house plan, that is a finalized, which is given in a software. Okay, so that house plan is nothing but here by using the RTL design, that means by using the Verilog HDL programming, we are designing the circuit diagram. Nothing but this house plan and this circuit diagram which we design in a software, both are same. Okay, now we got the soft copy of house plan and soft copy of RTL design. Okay, now with this soft copy, you need to build your house, right? Without building a house, only with a soft copy you won't do anything, right? So whatever the plan engineer given the plan, you are going to implement same plan in a hardware level. Hardware level means the house. Okay, so for that purpose, same here also. The plan we get, we need to verify. Here we are doing the verification because whether it is correct or not. Even here also we need to do the verification according to Vastu, according to some rooms and all, whether they are kept properly or not. We need to do the verification internally. So here also we need to do the verification. Okay. After that, first thing, if you are constructing some house, first thing is a floor plan. So we need to take the floor plan where we put some sand, we put some rock, everything like a floor plan. Okay, base. Same here also, floor plan. Okay, like a base. Base means silicon wafer. Okay, and after floor plan, we need to start construction of house, like by using the bricks. We construct every room, right? Bed, like a kitchen or hall, whatever. We construct every room in an organized way. Whatever the plan we got according to the engineer, whatever the organized way is there, according to that we need to place every room. Same here also, we need to place all the blocks in a SoC level, the processor, memory blocks, some sub modules, IPs, everything we need to place here. Okay, next, clock tree analysis. Clock tree analysis means what? In house, after constructing rooms and all, we need to give some power connections, current power connections, everything we need to give, right? For different electronic components and devices, for electrical devices. So same here also, we use some clock tree analysis. Okay, like that. Just example I'm telling. After that, final house, like a painting, everything we get, right? Here also we get top view, tape out, everything. So if you see here, physical verification, static timing analysis means what? We need to check setup time, hold time analysis. Okay, routing in the sense connections. Physical verification in the sense whether we did everything correctly or not. That is what physical verification. And then tape out. Tape out is the final stage. It's a completed. So once paints everything completed, it's a tape out, right? It's construction is completed. Same here, tape out. Like this: routing, sign off, fabrication, packaging, testing, and chipper. Okay, clear everyone?
Yes, ma'am.
Hello.
Hello, madam.
Yes,
Yeah,
ma'am.
clear everyone? Do you have any
Yeah,
doubts?
madam, will it affected by artificial intelligence in future designing?
Artificial intelligence mean okay, what's your question?
Will it affect by AL?
That means designing without physical engineers, AI will design, you are asking, or what?
In writing RTL code.
Okay, okay. See, if artificial intelligence is writing some code, means how it is writing the code?
We are writing hardware descriptive language, right?
Okay.
In future, VLSI field.
I understood your question. You are asking like in future maybe whatever our engineers are there, will artificial intelligence replace the engineers? That's what you are asking, right? Hello.
Yes, ma'am. Yes, ma'am.
Okay. So for that question, suppose okay, how the artificial intelligence is writing the program? That's what I'm asking. Nothing but as a human, as a engineers are training the artificial intelligence, right? Whether it's a component or it's a application or it's any device, engineer is training that. Okay, suppose ChatGPT is there, how the ChatGPT is getting all the information? Because already we trained the ChatGPT, already we stored every data into the ChatGPT, right? So based on that only it giving the data for us. Whatever our engineers design the chat GPT, same information it is providing to all users. Okay, so whatever the meta or any AI application, we have a lot of AI applications in WhatsApp, Instagram, regularly we are using, right? So nothing but engineers train them. Okay, that is just a easy way of application for users. Okay, but artificial never replace the engineers. Okay, maybe the work will be the easy. We can do work easily by using artificial intelligence applications. Okay, so if you are doing some work in 2-3 days, means we can complete within a hour. That is what we can do. But totally it replaces means it never. Why? Because there will be so many manual verification, manual testings, okay, which can be done only by engineers. Okay, there are a lot of calculations will be there internally. So artificial intelligence never replace a common engineer, like a manual engineer.
Okay, ma'am. Thank you, ma'am.
Okay, any other doubts? So this is what the design flow, front end design flow, back end design flow, design verification, PD and the DFT. Clear till here?
Yeah, ma'am. Clear.
Okay. So next, what is the difference between ASIC chip and FPGA and SOC?
FPGA, it can be rewritable.
Okay. What about ASIC chips?
ASIC is confined to only a particular application.
Okay. For particular applications. Okay. So can you give me some applications on ASIC chips and FPGA chips? What are the applications of ASIC chips and FPGA chips? I think you have done some of the projects, IoT projects with the Arduino boards and all, Raspberry Pi projects or FPGA projects in your student level academics, right? And also we discussed till now the ASIC design flow. So what is the difference between ASIC and FPGA and SOC? So ASIC is nothing but application specific integrated circuit, whereas FPGA is a field programmable gate array. If you see the pictures here, first one is same as a processors, right? Whatever the processors we are using in our mobile phones and laptops or any digital gadget, in any digital gadget there will be a processor. Even ATM card also, whenever you are inserting the ATM card into the machine, there will be small gold colored pin chip is there. That is also a ASIC chip or like integrated circuit. Okay, so ASIC chip is nothing but the permanent chips, the permanent integrated circuit. That means once we dump the program into the physical layout, okay, we cannot reprogram it again and again. Suppose this is what ASIC design flow. Okay, so whenever whatever the mobile we are using, if the mobile damage for any reason, we can do some modifications. We can do and we can fix the problem, right? But if processor damage means we cannot fix that problem. Okay, why? Because it's a one time programmable, that is programmed by the at manufacturing unit. Okay, so it is a one time programmable according to the specification. Suppose iPhone processor is there. Okay, if iPhone processor is it reprogrammable again and again means we cannot, because it's already reprogrammed. It's already programmed according to its specification, according to its architecture design. That architecture design is specially designed for the iPhone processor only. Suppose if any Intel processor design is there, that processor design is specially for the same processor design. We cannot use that Intel processor design to the iPhone, right? In the same way, ASIC design chips means only for specific applications. We use the ASIC chips. So once it is programmable, we cannot reprogram. That is done in the manufacturing companies only. Okay. And coming to the FPGA, FPGA all the free field programmable gate array. That means these all are boards. So if you see IoT, if you've done some IoT projects, Arduino boards will be there, and some embedded systems, Raspberry Pi boards will be there. Like that, here field programmable gate array is a board. Okay, so students can use the board to do some projects. It is a reprogrammable. That means once we dump the program, if any mistakes are there, if any errors are there, or if you want to use for multiple applications, we can use for multiple applications. Okay, so it is a reprogrammable. Suppose you designed a FPGA for traffic light controller hardware, so it works as a traffic light controller because you write the program according to the functionality and we need to dump. So after, if you want to design a elevator using the FPGA, you can design the elevator or any digital clock, digital alarm. You can reprogram it again and again. Okay, even in the companies also, most of the projects use FPGA to check, because without we cannot directly dump the program into the ASIC chip without doing verification, right? Because it's a cost, very high cost. The processors, everything, manufacturing process, everything is a high cost and also time taken. Okay, so that's why first we check the into the FPGA. Okay, and then if FPGA works properly, the functionality works properly in FPGA, then the design is going to be dumped into the silicon permanent chips. Okay, so that is what ASIC chip and FPGA chips. Is it clear, everyone?
Yes, ma'am.
Any doubts? Please ask. If any doubts are there, we can discuss. You can do some FPGA related projects if you are in third year or second year BTech. That is the best time to do FPGA projects.
Microcontroller.
Microcontroller is also good, but it's an embedded system related, right? If you are looking for VLSI, you can work on FPGA projects.
Ma'am, I have a doubt, ma'am.
Yeah.
What's the best EDA tool for front end design and Is it like Xilinx Vivado or Xilinx ISC, or is there a better tool for designing the front end stuff like that?
See, for verification, design and verification, any tool is same. Even if you go for commercial license version or free tool, everywhere we do the simulation and we check the output only, right? So for design verification engineer, we should have a good knowledge in writing the test cases, test plan, how we can develop the test feature wise test plans. Okay, so coding, how we can write a logical coding in a simplified ways. Okay, so that is very important. Tool you can use. There are free tools like a Xilinx tool is there, Model Simulator, Questa Sim, Vivado, Quartus Prime for synthesis. There are multiple tools. But for physical design, tools or commercial tools, licensed tools are important for physical design. Why? Because everything we do in the tool only, right? There will be lot of features in a licensed tools. Okay, for DV, any tool is okay, but coding, how to write the coding is very important. Even in interviews also, no one will ask about the tool for DV engineers. Just they will ask what tool you worked, but not in depth of tools. Okay, so they will ask how the programming, how you are writing the program. Some coding problem statements will be given. So according to the problem statement, how you are writing some coverage reports, and assertion based verification is very important for even if you are fresher, don't think like you are a fresher. You need to learn as an experienced engineer only. Okay, because industry requirements are in that level. Okay, so whatever you are learning, try to learn in a project level. Everyone need to implement at least 2 to 3 projects. Okay, in VLSA protocols are very important. And in PD also, projects, any 2 projects are important. Okay, side courses, if you are taking a training or if you are learning yourself, side courses also will be there, like computer architecture, CMOS design, STA design, those are also important. Okay, so
Yeah, ma'am.
any other? That's it. Okay. Next, system on chip. System on chip design we will discuss in some other session. See, system on chip is nothing but ASIC chip is there. It's an application specific integrated circuit, right? So same as but in ASIC chip, in if you see a computer CPU central processing unit, CPUs will be there. In that there will be a motherboard. In motherboard there will be a processor. Inside upon a processor there will be a fan to decrease the heat. Okay, for heat reduction, and there will be some graphic cards. We need to integrate the graphic card separately. In olden days, so old computers, if you are a cameraman persons or video editors, they only buy the graphic cards and they integrate. Normal usage not required, right? And there will be PCIe slots, not bridge IO, south bridge IO, different memory blocks will be there in the motherboard, PCB board. But coming to system on chip, nowadays it's not a trend of ASIC chips. Nowadays everything system on chip, multi-chiplet, monolithic. So there are lot of things. Okay. So system on chip is nothing but where we integrate all the circuit in a single chip, not in a board. Okay. So if you see here, these are the subsystems we call. Subsystems in the sense different blocks. Suppose here CPU subsystem is there. In CPU subsystem there will be n number of core. What is meant by core? What is the use of core? What is the use of core in a processor or in any circuit?
To increase the speed, we increase the cores like 4, 8 cores so that the pipeline is and data travel fast.
Okay, so if there are more number of cores, the processor speed is more because multitasking, one core do two tasks. So then two cores will do four tasks, three cores will do six tasks. Okay, so compared to octa-core, quad-core, dual cores, like that we have a n number of cores in the mobile phones and the laptops, right? So based on the number of cores, the performance will be increased. Okay, so if you see i3 laptops, i5, i7, like that, there are generations. Generations means i3 will have less performance in terms of speed, in terms of battery, everything. So i7 have more storage, more performance, more backup power. So everything is more because cores, there are more number of cores in i7. Okay, so core in the sense it do multiple tasking. Okay, so instructions, it run multiple instructions like how the user requirement is there. Okay, so next another subsystem, some safety related subsystem, machine learning subsystem, and these orange colors, those are nothing but interconnects. Okay, interconnects in the sense we connect a one block to another block because communication is needed, right? A one block to another block. In design verification, we have those protocols. Protocol knowledge is very important. Okay, every company have the requirement in the job description, like protocols. There are different types of protocols according to your experience, according to your uh, learning. You can start with the basic protocols to advanced protocol. Nothing but protocol means what here? Suppose there is a processor and there is a Wi-Fi module here. Processor to Wi-Fi module, you need to communicate. Okay, processor to graphic processor, you need to communicate. Processor to memory, you need to communicate. Okay, but that communication is different for every different blocks, right? So we cannot say the communication is same, the processor to graphic processor communication is same, the processor to memories communication is same, processor to Wi-Fi communication is same. We cannot tell like that. Why? Because Wi-Fi module is a small bandwidth, it works at a very low frequencies, but processor is a high frequency, it works at a high frequency, high speed, and also more data, it store more data. Like that, memory also, it store more data and works at a high bandwidth. Okay, so to communicate with a high to high, high to low, okay, like high to medium, like the protocols are divided. Protocol in the sense rules, we need to follow certain rules, whether it's a parallel communication or serial communication, half duplex or full duplex, or like a intra communication system or inter communication system. Intra and inter communication system means suppose our mobile phones are there. Okay, mobile phones we will integrate with the computers, right, by using the USB cable. Everyone know USB cable, C type cables, right? What is that? That means outside the block, outside the device is communicating with the internal processor of the laptop. Okay, so that is what intra communication system. Inter communication system means within the SOC. These are high level things for you at this stage, but I think there are few experienced persons also there, like who completed the graduation, so they can understand. Okay, so if you are communicating with the internal processor to some IP or some one block to another block in internal chip, then we use inter-system communication protocols. Okay, like that, high speed communication, low speed communication, bus protocols for parallel communication, we follow certain rules. Okay, so that is what system on chip design, where we have subsystems, IPs in SOC level. Okay. Once you go to the industry, you will get the projects like IP verification, SOC verification engineer, ASIC design engineer, like that. Okay. Is it clear, everyone? This is how the SOC looks after design manufacture. Any doubts?
Ma'am, what an ASIC design engineer do in industry level?
design engineer will design RTL design, RTL programming in micro architectural level. Okay, architectural level is different, micro architectural level is different. Suppose you are taking a multiplexer. Okay, so multiplexer have the circuit diagram with a n number of gates, AND gate. Suppose 16 by 1 multiplexer means 16 AND gates will be connected to one OR gate. Okay, so this is normal architecture. If you draw in a CMOS level, it also normal architecture, but micro level architecture is different. Okay, so that thing you must know as a design engineer. But for verification engineer, SVUVM enough. SVUVM, you must have deep understanding.
Okay, and which type of verification engineer is good, like memory verification or SOC verification?
See, that thing we cannot know as of now. Once you go to the industry, we don't know what project they will allocate, right? Based on that experience, for next level, you need to move on. If you get the project related to the memory, so you have the memory experience, memory verification experience. If you got the project related SOC design debugging, so you will get that experience. So next, whenever you are shifting to some other company, you can put that experience. But as a fresher, you need to start with a either DV role or PD role or DFT role or some layout, these type of basic roles. Okay.
Okay, ma'am. Thank you.
Bro, for fresher, salary, how much can get for in TV, physical, VLSI?
See,
And
VLSI means always for freshers there will be less package only. You don't keep the expectations like you will get 10 plus package, 15 plus package. Okay,
no,
maybe
this is
you
the
will get if you are from IIT, NIT. If you try with a product based company, definitely you will get that. Our last NIT Kurukshetra students package 33 lakhs and 23 lakhs package before I worked in semi design, right? 4 years. So we got that package. But for normal colleges, autonomous college students will be there. Their package will be around 4 lakhs, 5 lakhs, like that. Okay, for even for verification or PD, VLSI engineers have less package only. You need to start with a less package. Don't have high expectations. Once you go to the industry, once you get a very good experience on projects, then you can expect a minimum 20 lakhs package for two plus year experience. Okay.
oh, come on. Thank you.
Yeah.
But can I get trained VLSI?
Okay.
This Pro Logic, is this only teaching or company?
It's not a company as of now. Maybe in future. So as of
Yeah,
now, it's finding in placements.
this is only for training, right?
Yes.
Yeah, thank you.
Okay. Any other
Ma'am,
doubts? Yeah.
what are some of the protocols that we can learn to basically the important protocols that can be learned by a fresher?
So for design verification, in design verification, we have different protocols like UART, I2C for freshers, UART, I2C, AMBA protocols, APB, AHB, AXI. These protocols are most important. For experienced engineer like Ethernet, PCI, USB, um, those are enough. JTAG. JTAG is very special case. It's not a common protocol. Only few of the industries use JTAG.
Okay, ma'am. Thank you.
UART, I2C, APB, AHB, AXI. You can note down. Okay. Any
Ma'am,
other
can you please
doubts?
repeat it once again?
UART, I2C, APB, AHB, AXI. SPI also, if you are interested.
Okay, ma'am. Thank you.
Any other doubts? Everyone here?
Is this a daily or a weekend session for learning?
It's a regular sessions. Weekly 3 days sessions will be there. 3 days live sessions. Alternate days. 1 day live session, next day assignment practice, and then live session, and then assignment practice, again live session, assignment practice, in that way.
Need to pay any fees for this?
Yeah. We have different job oriented courses. So design verification, physical design, and DFT courses are there. In physical design, we are providing, let me share my screen. This is what the curriculum for ASIC design verification course. So in ASIC design verification course, we are providing total 6 modules. Module 1 is advanced digital electronics. We don't discuss basics of digital electronics because everyone know the basic things, right? What is meant by combinational logic circuit, sequential logic circuits, FSM, everything. We focus mostly on interview point of thing, like assignments, mock tests, mock questions. So that is what advanced digital electronics. There will be regular sessions, but not from basics. We will discuss mostly on interview point of thing. Next, module 2, Verilog HDL, RTL design using Verilog HDL. That one we start from basic onwards, from scratch to project level. Regular live sessions will be there. And module 3, system verilog for verification. System verilog for verification also from scratch to project level. We will implement projects. Okay. And module 4, UVM for verification. And module 5, scripting. Module 6, design and verification projects. Here is the detailed structure of each. In demo session, first we will cover VLSI design, what is front end, back end, different these are different things. And module 1, what are the advanced topics of digital electronics? All topics like combinational, sequential, shift registers, counters, FSM. Practice is very important. Why? Because we need to crack the general test first. There will be an entrance test, right? In entrance test, most of the questions will be asked different logical questions. So for that purpose, we mostly concentrate on interview point of view only. And static timing analysis, CMOS design. Every engineer must know these topics, at least basics all. Okay, so that's why we cover STA and CMOS.
Yeah.
And these are some of other topics. And in RTL design using Verilog HDL, we start with the basics. What is a data type? What are the applications, operators, description styles? Everything we discuss in a theory plus lab sessions. Same. However, today's session is there. We will discuss theory, example. We will implement in a tool. That's what lab sessions. So we will cover all the combinational, sequential, FSMs, counters, everything proper way, structured way. So this is how we structurized our program. For learners also, it is very easy to learn, and they can easily grab all the concepts in a one by one in a format. Okay, so first synthesis, how to write the test benches, then for all combinational, sequential, flip-flops, counters, FSM, memories. Okay, so coding everyone can write. Verilog program is very easy, but how how we can write a simplified way, optimized way, that is very important. Okay, suppose there is a multiplexer, means multiplexer can be written in a 20 lines, 30 lines, 10 number of lines also. But how we can write a multiplexer in a single line logic, 2 lines logic? Even if you take any type of multiplexer, whether it is a 32-bit or 64-bit, 128-bit, how we can write a single line code for full adder, ripple carry adders, registers, how we can registers and counters are very important in a DV. Why? Because in not only Verilog HDL, in system Verilog also we use registers, counter, logics. Okay, so how simply we write the program, that is very important. So FSMs, multiple models of FSMs, how to design memory. Here we have some minor projects in memories, like how to design the FIFO, RAM, ROM. So everything we will discuss, coding and the implementation in the tools. And then how to write the test case concepts from basic to pro. Okay. So this is, there will be regular assignment. After session, there will be assignment. You need to submit. We will give 1 week time for the assignment. Within a 1 week, you can submit the assignment like that after each session. And then system Verilog. System Verilog also, from all basic topics, I will share you the course structure, everyone. You can go through the structure and I will share in the group also. Okay. If you are not in group, you can contact me directly. So this is what system Verilog verification. We will cover advanced level of verification concepts. Okay, like a coverage analysis. Coverage is very important for verification engineer. How to design our own test cases, coverage analysis, assertion based verification. How we can use object oriented program in a practical way. Okay, how we connect in an industrial way. Most of the trained freshers, you can take the review also. I'm not telling my from myself. You can take the reviews who completed a training from different institutions. Just ask how the OOPS concepts are applicable in real time. Definitely out of 10 members, 9 members doesn't answer the questions. Okay, because that is what the basic things they learn. But in our course, we will explain everything in terms of real time use case. Okay, suppose object oriented program is there, how we use a encapsulation in a real time, how we can use polymorphism concept in a real time application to design a protocols or projects. Okay, like that coverage, assertions. So everything we cover in an advanced level. And these are the most important topics in system Verilog. How to write the test bench components, test plan, test cases, and there will be regular assignments, mocks, and UVM. UVM also we will cover advanced level. Okay, so everything in theory and the lab sessions. So these are all the topics. You can go through the all topics. Same structure wise we planned. And scripting language. Scripting language also we have some advanced topics which are used in industry level, like importance of regressions, how to run the regressions, how to check the test pass or fail, how to debug the test cases in SOC level, IP level, like that we will discuss. And module 6, projects and protocols. We are providing 6 industrial level protocols, and 3 major projects. Okay, protocols are YOT. You can see the detailed information here. YOT, I2C, AMBA protocols, ABB, AHB, AXI, and 3 major projects like DMA controller, router, digital alarm, traffic light controller, 4-port calculator, RISC-V project, and there are some advanced protocols. So from these projects, you can select your own project. Whatever the project you want, you can select. So based on that, we will allocate. Okay. So this is what the structurized program from our team. Um, Same for physical design also same. Tomorrow we will post the brochure for physical design. So if anyone interested, you can contact me. But compared to the most of the institutions, we are charging very affordable price for students. Okay, you can inquire. You can inquire the institutions or any whatever and then only you can contact us. Okay, I can say strongly that because from last 2 months I am getting lot of reviews from all the students who completed the training from various institutions. That's why I can say strongly, you can compare with other institutions, brochures, pay whatever the price. Then only if everything good in our institution, you can join. Okay. But if you are interested for self-learning, you can prefer self-learning also. But you must have proper structured plan and dedication, because if you get the doubts and all, the projects you cannot do your own. At least you can learn some basic if you are interested in self-learning. But if you want industrial experience, then training is very important. Even if you learn self-learning, once you go to the any interview, they will ask training experience or internship experience, certification experience. So based on that, you can decide. Okay. Any other doubts,
For
girls?
how your help job.
No, sorry. Something you are asking? Okay, that's it. Huh?
Hello.
Yeah, please
So, for job, how your help after trend?
Uh, for a job, for training, for placements, we are going to start the placements from 4th month onwards. Okay, so training duration is 5 to 6 months, right? From 4th month onwards, we are going to get the placements. So it's a starting stage, right? So we are collaborating with the companies. We are talking with the companies, mostly both the product based and the service based. Based on your, if you are from IIT background, NIT background, mostly product based companies will hire. If not, we have good service based companies also. Okay. But nowadays situations are tough, but we are trying our best. Okay, I am personally trying our best to get the good placement, because quality training is very important. My main motive is to provide the quality training which meets the industrial experience. Okay, because you are spending the amount, you have a lot of expectations on your career, right? I know that thing. Every student have lot of expectations on their careers. So whenever they are spending some time, some amount or whatever the time, we need to give some judgment to that, right? So for that purpose, so that is my main motive, to give in affordable prices and very quality training with the placements.
How much, madam? Price
Excuse me.
fees?
Price for job oriented program, we are charging 50,000.
Uh-huh.
Yeah, that's the most affordable compared to most of the institutions which I get lot of reviews. That's why I'm telling strongly. Yeah, please tell.
One last doubt is like PD engineers are doing floor planning and all, na? So
Yeah.
this can be automated by OpenLane and Skywriter. Like these are the free source resources I have used. So what exactly the PD engineers are doing in industry, because they can be automated floor planning and STA, CTS.
PD engineers, they are working with the technology nodes, right? There are multiple things. We cannot say only how the industry is working, only one thing. There are multiple things. Even you are telling everything is generated automatically, right? Even it's generated automatically. Every test, every if you see DFT, there will be n number of scan chains. Even for PD, there will be floor plan or placement. There will be n number of signals. We need to check every node to node. For that purpose, manual interaction is very important. Manual doing calculations are very important from engineers, right? Even it's everything generated automatically.
Yes, actually, in in Cadence, while doing layout, we are putting every modules, every devices on plates and wires. But while RTL to GDS, we just give commands like floor planning and CTS, and they do and give them because it are so minute. So, what exactly the PD engineers do? Like a
Um,
lots of millions of gates are there. Every routing can't be done now.
Yes, yes. Mostly in PD side, we do entire flow. That flow also divided into various parts. Only one person cannot do all the parts, right? So based on whatever the specification we have, the requirement of specification, we do the calculations according to that in a layout level or in a final level, whatever. So PD, I don't have much experience, frankly, if I say, but we have a good experienced engineers in PD who are working in a product-based companies with a 10 plus year experience. We will connect with you with them. Okay, so you can ping me once, you can talk with them. So you will get the clarity. Okay.
Okay, thank you so much, ma'am. It was so interesting and
Okay.
idea. Thank you.
Yeah. Okay. So if you don't have any doubts, we can close.
Madam, how it is different from software like IT to this VLSI design, madam?
There is a lot of difference in software to IT, VLSI.
Uh,
See, software,
scope,
I cannot
package,
say software is not good. Whenever you have a very good coding skills, then only you
yeah,
can prefer the software. Without coding skills, if you go normal jobs like a white collar jobs, it never impact. Okay, so once you if you have very good coding skill, hacking skills like where you use hacker rank code chef platforms, then you will get placed in top MNCs. So that jobs will be good. Okay, but compared to that, if you spend first 2 years in VLSI as a fresher, next whenever the experience is increasing, you will get lot of opportunities and packages also very good in VLSI. And VLSI is one of the booming technology in next 2 to 3 years, right? So definitely you will have high paid jobs. So if you step into the VLSI from now itself, next 2 to 3 years, you will get good experience. So from that, you will get very good packages, right?
yeah, ma'am. Thank you.
So IT and VLSI are totally different. If you don't have coding knowledge, don't prefer IT. If you don't interest in coding, you can prefer VLSI.
We are looking for only which in which field better scope. So that's
Which year passed out you are?
2022, ma'am.
Then DV is good.
DV, yeah.
Yes. For freshers, fresh passed outs only, I prefer PD because for late passed outs, yeah, because we don't have openings, right? That's why I'm telling.
Okay.
Okay.
Yeah, thank you.
Yeah. Okay. Okay, then thank you all.
Thank you, ma'am. Bye, ma'am.
Yeah.
Thank you, ma'am.
Thank you.